Assalamu alaikum everyone. This is 8886701 Nonlinear Control System. This is the first class of this course. So at the beginning, let us know the textbook that we are going to follow mainly in this uh, course is Applied Nonlinear Control by Slot and Lee. Uh, I will try to upload I'll check whether there is a soft copy available or not. If it is available and if copyright rule allows, then I'll try to give it in the Google Classroom. Now, for this one, today we're going to actually start the chapter one. Chapter one is very basics of the course as discussions, few fundamental questions we are going to answer, like why nonlinear control, what types of nonlinearities are there. So all these kind of fundamental questions we are going to discuss. This class will be a short class, as well as it will have very less mathematical thing involved. So first of all, let's discuss what is the subject the nonlinear control actually deals with. So the first thing it actually works with is basically analysis and the design of the nonlinear control system. So bottom thing, what we are doing is analysis, analysis and design of non-linear control system. At times, allow me to actually use these short notations so that I can cover things more. So, what does it mean actually by a non-linear control system? This is also a question. So, what is mean? So, it means that at least we have to have one nonlinear component present in the system. So, any control system having at least one nonlinear component is known as nonlinear control system, and this subject deals with analysis and the design of this nonlinear control system. Okay, so what do we mean by actually designing is to obtain systems desired characteristics. So desired characteristics. So some of them, can you tell me some of them? So basically, your settling time, rise time, then about the stability, steady state error. So these are the common control system specifications. So as a control engineer, our task is to actually construct a controller that will give us those desired characteristic for the closed loop of the system. Okay, so in nonlinear control, design and analysis actually linked. So design and analysis, basically, I think analysis should be written first. Analysis and design, they actually linked too much. So because we have to apply the interactive process to figure out the final version of our controller. So that is why we'll have to do the deep analysis, then again designing. If the design is not according to the desired specification or the characteristic, then again go for the repeated iterative process. So that is why they're linked together. Now, first question we should actually go for is why nonlinear control? Because we have classic control, which has been used for centuries, more than centuries now. Then why actually we need a linear control, nonlinear control? So the answer to this is actually nonlinear control is more powerful, and it actually deals with, it provides us lot of advantage over the over the linear control. So let us try to explain some of those. So uh, why nonlinear control? So the first point is improvement of existing control system. Okay. So in existing linear control system, what we actually do, we do our control methods. We apply the control methods based on the key assumption that we have only small range of operations. So we linearize in a very small domain of operation, and around that small zone, actually try to operate the system. But in most cases, it seems that if we have the nonlinearity involved, so then this controller lose its precision. So that is why it is always better to go for the nonlinear control, which allows us a large range of operation directly. Okay, and also once those nonlinearities doesn't actually, the nonlinearities actually become very dominant, like in case of your speed of motion. So in case of, say, you're designing a robotic arms or robotic limbs. Okay, so the speed is important there. So as the speed increases, some nonlinear terms like centripetal forces or Coriolis forces comes into. Okay, so Coriolis and centripetal centri petal forces come, who actually these forces are proportional to the velocity square. So if the velocity is increasing, so these nonlinear forces will be dominant. In that case, what we are going to see is that they're actually moving away from the uh, control technique more. So it will deviate more, so it will give us less precision in terms of the output. So says tasks like pick and place or welding, laser cutting. So all these things which actually will have less output. So basically we cannot increase the speed. If we increase the speed of the processes, then these forces increases. So our output is becoming lesser. So productivity also reduces. Okay, so for these reasons, productivity is also low because we have to operate at low velocity, because if we operate at high velocity, then these forces will be dominant. So actually we have to compromise the productivity. So, but these nonlinear forces can, in the robotic motion actually can be fully compensated by the nonlinear control technique. So our productivity can be increased if we go for the nonlinear technique. Okay, so this is first point why we actually can go about the nonlinear control system. Even though we have a very rich linear control system which has been followed for over a century. Now the next thing is the second point is analysis of hard nonlinearities. Okay, so analysis of the hard nonlinearities. What does this mean, hard nonlinearities? Because these are actually represent the discontinuous nature that actually helps hurt us to actually use, that actually prevent us to use the linearization approximation. So discontinuous nature of the nonlinearity. Okay, what are those? Maybe the some of them we discussed, that saturation, backlash in the gears, or hysteresis. Okay, so all these are having a uh, very sharp changes, basically discontinuous nature of the mm, non-linearity, and that is why they are actually known as hard non-linearities. And in case of the hard non-linearity, what is the problem? The linear approximation cannot be used. So there is no other way for this kind of hard nonlinearities. It cannot be represented or compensated by linear control system. So only thing that we have is to apply the nonlinear control system for this kind of system. And if we have this kind of nonlinearities, frequently actually they cause undesirable behavior of the control system, such as instability as well as limit cycles. Don't worry, what is limit cycle we'll be discussing shortly. So these effects must be predicted, and there has to be uh, properly compensated, and that compensation cannot be done by the linear control. So we have to go for nonlinear control for these cases. So this is number two. Number three is dealing with model uncertainty. Okay, so what does it mean? Say a linear control system, we always assume that we know most of the parameters of the system. So and based on that actually the linear controller is designed. So sometimes it may happen that some of the parameter is very slow changing with time. So this can be one way, or suddenly it can have a very rapid change, so which is not actually counted while we are actually designing the linear controller. So because of which it can actually, because of this inaccuracy or obsolete values of the model parameters, actually it can have a large degradation of the performance, or eventually it can also bring instability. So for this kind of thing, actually for compensating the model uncertainty or parameter changes, actually we have to intentionally introduce nonlinearity into the controller as a part of the control system to model this uncertainty. Okay, so that we can actually compensate those. And two commonly used nonlinear controller for this one is known as robust controller, and the other one is known as adaptive controller. Okay, so these are commonly used two nonlinear techniques. So intentionally we introduce some nonlinearity into our system so that actually compensate for the uncertain values of the system parameters. So this is the third one. Then finally, the fourth one is design simplicity. Even though it is difficult to understand the nonlinear phenomena and their behaviors, but at the end it is inherent, and because of which it is also easier to implement the controller, nonlinear controller, compared to the linear controllers. Okay, so this is one of the inherent property of nonlinear controller, because these controller are often deeply rooted in the physics of the plant itself. So it makes it very easy. Like you can consider the case of an inverted pendulum. So you can find out the equation and everything and find out the eigenvalues, but these eigenvalues will actually carry any information that will help us to compensate this system or design this system. Rather, actually, by looking at the system, as we know, whenever the inverted pendulums will reach the minimum energy state after dissipating all the energies, then it will be stable. So these basic fundamental ideas actually make things simpler to implement the nonlinear control. And apart from this, there are a few other things always there. There may be the cost. Cost is a huge burden, and also the performance optimality, how much performance or performance specification you can call. Now about the cost is basically when we are designing our control system using the linear technique. Actually, we are doing it for a small zone of operation. So in this small zone of operation, we always have to keep our controller in this small zone. So for that, whatever whatever the sensor we are using or whatever the actuators we are using, they has to be very precise. So that is why we actually have to use some expensive expensive components for linear control design. But because of the fact that we are using a large range of operation in nonlinear control, so we don't have to be that specific about these sensors and actuators. So it actually can be, we can use less expensive components for your nonlinear control design. Okay, so this is the advantage that we have. And also, since we are allowing the nonlinear control, the range of operation is broadened, and as well as the output will also be, will have productive outputs as well. So one and another important aspect of the nonlinear control is the automatic control. So you have to make it somehow automatic so that these nonlinearities, these uncertainties, those or the range of operation, those can be mitigated automatically. So for that, we actually have to know the fundamentals. We have to have the sharper knowledge of these concepts, the systems knowledge, as well as the nonlinear controllers, so that actually our conceptually we can make it easier. Now, uh, previously, why the nonlinear control was not that popular, one of the reason was we have very less computational power in past, and because of which most of the problem could not be solved by hand or calculator, something like. But now we have a very powerful computers. They can actually process the system very fast, and because of this advancement, actually nowadays it is the demand of the nonlinear control is increasing, and the field is actually rising. And hardly any physical controller we have to implement nowadays. If you go for digital implementation of these nonlinear controllers, only the computational part will be carried out, the controller part is carried out by the microprocessor, then it just generates the output or the control signal that actually drives the plant. So it's become a lot easier nowadays, and that is why this nonlinear control is now gaining more popularities. So the next article is basically 1.2 nonlinear system behavior. So article 1.2, whatever we discussed is up to that is article 1.1, and which was actually the why we try to answer the question why actually we are going for nonlinear controls system. Now this one is 1.2, that is nonlinear system behavior. Okay, so what nonlinear system behaviors we have? As you said, at least we need to have one component, so that we have to understand, and then we have to realize the types of nonlinearity. There is uh, can be classified into two, as inherent. Okay, so inherent or natural, or we have intentional or artificial. Okay, so some of the naturally available in the plant or system. So this sort of thing is called inherent, like your centripetal force in the rotational motion, or column friction between contacting surfaces, so friction between the surfaces. So all these things are actually inherently available. And in some cases, as we already given some example, that to compensate the model uncertainty, we have to uh, we can use some, we can introduce some nonlinearities. So those are called intentional nonlinearities, and those intentional nonlinearities or artificial nonlinearities are actually introduced by the designer. So like adaptive control law or bang optimal control law, all these things can introduce artificial or intentional nonlinearities. This is one way to see at the nonlinearity. So there is another way that is called, this is one type maybe. Okay, so the next type of classification based on their continuity. So they are called in terms of magnetic properties as, sorry, mathematical properties as continuous and discontinuous. Okay, so because the discontinuous nonlinearities cannot be locally approximated by linear functions, so that is why these are also known as hard nonlinearities. Okay, so naturally the other one is called soft nonlinearity. Okay, so this is about the example of the hard knowledge we already have given: backlash, hysteresis, stiction. So all these are commonly found in the control system. Okay, so a small range of approximation and the large range of operations. So they will have different effect on your control system based on whether they're actually continuous or discontinuous. Now, let us see the definition of the linear system. So we know that we need to have superposition as well as two properties we have to follow. The first one is superposition. That means separate input, whatever the corresponding output they are giving, the summation of the summation of the input will give the summation of the output. Also, the homogeneity rule that says that if you multiply the input with a constant, then the output will also be multiplied with the same constant. So all these actually uh, the properties given based on your linear control theory, as well as in the state space we can also have similar criteria. So let us try to see what is meant by linear system in terms of the state space representation. So in terms of the state space representation, we represent the system by x dot equal to ax. I think the chapter 3 of uh, control system engineering, that is by NICE, Norman as NICE, we already introduced how to represent it. So in this particular case, I think so far, if you can recall, we learned something like this: x dot equal to ax plus bu. So this is your system matrix, this is your input matrix, so this is your input. So if you are just talking about only the system, not about the for input, so then this is what we have. So now x is being the state and a is your system matrix. And for a linear time invariant system have the properties, following properties. Number one is a linear system has a unique equilibrium point if it is not singular. So it has a unique equilibrium point. This is one. Okay, so this is one. Then second in is the equilibrium point is stable. So equilibrium point is stable if all eigenvalues of a, if all eigenvalues of a have negative real part. Okay, so and one thing also has to be mentioned is regardless of the initial conditions. Okay, so next property that we have is the transient response of the linear system is composed of the natural modes of system. Okay, in general, the solution can be solved analytically. So it is inherent. So response is natural response. So response is natural mode. Actually, as you can see, because of the fact that it is actually representing only the system, so it has to be the natural response, uh, without any doubt. Next thing is the if you have input, then your system will be represented by something like this: x dot equal to x plus bu. In that case, we have to I have to introduce few more properties. Firstly, it has to now, if you have input involved, now the superposition thing has to be there. So one thing is superposition. Superposition, as I said, different input. If you have different output, then if you add the inputs, then it should have the addition of the outputs as well. Okay, and secondly, the bounded input should give you bounded output. That condition has to be also there. So the condition of the stability is bounded input should give you bounded output. Input gives bounded output. Okay, so for the stability, and thirdly is if you have a sinusoidal input, so it will have sinusoidal output. Sinusoidal input will give sinusoidal output. Okay, so the of same frequency. So this is one of the critical thing of same frequency. Okay, so you have to be careful about the frequency will only be changed if you have a nonlinear system. If you have a linear system, then frequency should have changed, should be remain unchanged, and also there may be some phase difference between the two signal, but the frequency cannot be changed. Now let us look at one example of a nonlinear system. So this is example 1.1, a simplified model for motion of an underwater vehicle. So simplified model for a motion of the underwater vehicle. So basically V dot equal to V dot plus V square uh, equal to U. So U is the input, and this is your velocity, and this is your velocity square, which in this case is our nonlinear component. Nonlinear component, and this is also known as square law drag. Okay, so mechanical terminology, and it actually prevents us. It actually introduces the nonlinearity in the system of your underwater vehicle. Now, how this is nonlinear? If we try to analyze this one, so we can see that the systems are faster in response to the position unit state. Okay, so now let us try to solve with different conditions given, like input conditions. So how the system is going to behave. Okay, so based on that, we'll try to realize what kind of nonlinearity you have. Now, say you if you have your input is 1, so then what will be your output? Steady state output. So our steady state output will be, for the steady state, you know that v dot equal to actually dv by dt. At the steady state, there should not be any rate of change. So basically, it should be equal to 0. So as you can see, our output will be v square equal to u, and u is 1. So v will be actually root over 1. Okay, so for a say unit step signal, so what we are saying that in this particular system, if you are applying a unit step signal for sometimes say for 5 seconds, so then what we are going to see in the response will be something like this. Okay, so gradually it will increase to 1 value. Okay, after that it will stay at the value 1 for 5 seconds. Then gradually it will also going back to 0. Okay, so this will be the type of the response. So bottom line is, what is your final value here? Final value here, if you have given value 1 in the input and you are getting a value 1 at the output. Now, what will be, this is your say input u, and this was your velocity output. Now, if your input u is actually can be thirst in mechanical thirst, and if your input is a 10, then what should be your final value you're achieving? So basically, v square is again equal to u. So v will be root over 10. So now our output is approximately say 3.2. So as you can see, for one input, we are going to a value 1 output, but for another input 10, we're actually going to some other value 3.2. So basically, these are values are not multiplied. Input, if you multiply the input, the output is not multiplied by the same factor. So basically, it represents a nonlinear system. So you're applying the value 10 here, what you are going to get in the output is 3.2, something like this. For 5 seconds, then it will be vanished. So this is your final value, 3.2. So final value was 1 in the previous case. So this is a nonlinear behavior. So because of the fact that output is not multiplied by 10 times, so the homogeneity is not been followed here. Okay, so next is let us try to look at some common nonlinear system behaviors. So some common nonlinear system behaviors. Okay, so first of all is multiple equilibrium point. I think it's better to change. Multiple equilibrium point. Okay, so a linear system has always a single equilibrium point, as we already defined in the properties of the linear system. But a nonlinear system may have multiple uh, equilibrium point. So again, say let us take one example. That first thing is, say, x dot equal to minus x. So this can be a linear system, and a nonlinear counterpart of this one is x dot equal to minus x plus x squared. So this term is actually the nonlinear term at present. So we can actually easily solve this one by your Laplace transformation. Uh, and before actually going for the solution of this one, we can also find out what will be our equilibrium point. So for the equilibrium point, as I said, x dot equal to dx by dt has to be equal to 0. So we can say that x equal to 0 is the equilibrium point for this one. And similarly, the equilibrium point for this one will be minus x plus x square equal to 0. So we can actually take common of x, then x minus 1. So x equal to 0 is one equilibrium point, and x equal to 1 is another equilibrium point. So multiple equilibrium point is possible in case of a nonlinear system. Now, if you're trying to figure out the solution, it is very easy to figure out the solution for linear system, because you can actually apply your Laplace transformation formula for that one. So if you take the Laplace transformation of this equation, then what we are going to get is x star s xs minus x0 equal to minus xs. So xs can be brought to the same side, and s plus 1 xs equal to x0. So xs equal to x0 initial value divided by s plus 1. So if you take inverse Laplace transformation, then what we are going to get here is xt can be written as x0 e to the power minus t. So simple solution. And if you try to plot it, if you try to plot this one, you're going to say is whatever your initial condition, say your initial condition is here. So we'll always go back to 0 as time approaches infinity. You are here, so you're going to follow this path. You are here, so you're going to follow a path something like this. So wherever it is, whatever your initial condition, it is always coming back to the equilibrium point. So this is how it works for a linear system. But if you have a nonlinear system as like this one, which has two equilibrium point, and its corresponding solution of this one, you cannot apply the the Laplace transformation, because of the fact Laplace transformation is only applicable to a linear ordinary differential equation. So our equation is not linear, so because of which we cannot apply the Laplace transform. So you actually have to apply the separation of the variable method. So eventually dx by minus x plus x square equal to dt, and then if you integrate and find out the solution, then you are going to get something like this: xt equal to x0 e to the minus t 1 minus x0 plus x0 e to the power minus t. Okay, so this is what we are going to get. So, and also if we plot the curve, what we are going to see is that there is two equilibrium point. One is 0, okay, and one is actually 1. So now what happens is any value lower than 1, so this is 1 and this is 0. So any value lower than 1, if your starting point is any value lower than, it will always go back to that stable equilibrium point. Okay, so any value lower than 1. But now what happens if you have any value higher than 1, it doesn't go to that stable one, rather it actually increases infinitely. So this is how your system is now becoming unstable. So there is a zone of your stability, there is a zone of unstable region. So this is what happens in case of the nonlinear system. First of all, the first thing that happens is you will have multiple equilibrium point as well as, okay, so one thing I haven't said what is mean by equilibrium point. It is also, I think I just assume that you know, but even if you don't know, let me define the equilibrium point. Equilibrium point is a point where the system can stay forever without moving. Okay, so this is a definition of the equilibrium point. So let me just write it. And point is a point where the system can stay forever. Why the system can stay forever in a equilibrium point? Because there is no rate of change involved in that point. Because whenever we're finding the equilibrium point, we always assume that rate of change or higher order rate of change, all these things are actually vanishing from the equation. Then we are finding. So if there is no movement available, no variation available, then the system will always be at that point. So it will never try to come out of that point. Okay, so this is your equilibrium point. Now, some of the equilibrium point, as we already said, then can be stable, like in this particular example, 0 is a stable equilibrium point, but 1 is not a stable equilibrium point. So because once you have crossing that value of 1, it will always diverge from that point. So based on that, you have to decide which one is a equilibrium and which one is not an equilibrium point. And also sometimes you can have some function like uh, which actually involves your input with the system state. So they are called bounded external input. So basically in terms of state space, you can represent the system something like this x u. So they are bilateral, bilinear actually system. Sometimes it is possible based on the value of u, your system can be uh, can behave like a stable system or converging system, or can behave like an unstable system or divergent system. So let me give you an example. Say if our x equal, if our u equal to -1, then what we have is x dot equal to minus x. So we already solved this one, which have a solution something like this. Xt equal to e to the power minus t. Don't forget your initial value, that is x0. But if your u is now 1, then we have x dot equal to plus x, and now it gives you x t equal to x0 e to the power t. So now you have exponentially rising signal. So now that is why they are called bilinear system. So, and this condition is known as bounded external input. So bounded external input. Okay, so this is also a possible scenario. Now next nonlinearity is called limit cycle. So limit cycle. What is limit cycle? Limit cycle is oscillation of fixed magnitude and fixed period, basically fixed frequency, without any external excitation. So in some system, there is some oscillation available, which is of fixed magnitude and this fixed frequency. So this magnitude is not dependent on some other parameter. Always it will maintain the same magnitude. So these oscillations are known as limit cycle, or sometimes it is also called a self-excited oscillation. So limit cycle or self-excited oscillation. Okay, so one of the common example of this self-excited oscillation is Van der Pol equation. So the scientist Van der Pol actually invented this one. So this is mx double dot plus 2c x square minus 1 x dot plus kx equal to 0. Now, as you can see here, our rate of change is actually also dependent on the position here. Okay, so and now if the position value x is very high compared to 1, in that case, it will give a convergent solution. Okay, this term will be remaining positive, so damping factor will be also positive, and because of which actually the energy will be absorbed by the system. So this system can be actually a mass spring damper system where your position dependent damping coefficient is there. So basically, as you can know from a second order differential equation, what we have s square plus twice zeta omega n s plus omega n square. Okay, so this is your generalized second order equation. So as you can see, this twice zeta omega n, here you have damping. Now this term twice c uh, x square plus 1, this is actually your equivalent to twice zeta omega n. So this is actually position dependent damping coefficient. So, and because of which, if the position is higher than 1, so this dependent, the variable will be actually positive in number, and because of which your damping will be positive and your system is going to absorb energy. Now, if the value of the system, value of the x is smaller than 1, in that case, the damping coefficient here will be negative. So zeta is positive. Here zeta is negative. Negative damping means actually now the system is supplying energy to the ambient environment. So this sort of thing will be happening back and forth. So energy, sometimes it will be giving some energy, sometimes it will be returning energy based on the position. So this is what is called a self-excited oscillation, which can also be possible in case of our RLC electrical circuit if you have a nonlinear resistance. Okay, so this is called Van der Pol equation, and this oscillation is there. Now, one thing we have to be careful, as we already says, this oscillation is obviously uh, unique. Unique in a sense that their amplitude is independent of their initial condition. In case of our natural response, there's some other oscillation is also available in the system. Don't get confused about that one. If your system is marginally stable, we know that from the control system engineering perspective that we have actually roots in the j omega axis. So j omega axis is producing a marginally stable system. Marginally stable system or pure oscillation. So the difference between this marginally stable signal or pure oscillation with our limit cycle, the difference has to be understood. The first thing is amplitude is constant here. Amplitude is constant, where it is variable in case of the marginally stable system based on the initial condition. Okay, and marginally stable systems are also uh, sensitive to the changes in the system parameter, but it doesn't make any difference. Whatever the parameter you're changing in your system, it is always remaining. So limit cycle have no sensitivity of system parameter change. Okay. So these are the two difference between marginally stable oscillation and pure oscillation with the limit cycle. And as you can see, some of the limit cycle is naturally available in or inherently available in the nature. So and sometimes it is needed to be removed because in some cases, like in the aeroplane, if you have some sustained oscillation limit cycle, it can be dangerous for the passengers, for the aircraft, so it can collapse. And because of those, it is undesirable. So limit cycle sometimes is desirable, like in the laboratory, in the electrical or electronic oscillation, which we can produce to actually do some experiments. So those are desirable. So limit cycle can be desirable, or at times it is undesirable. So we actually have to understand the fundamental idea how the limit cycle is generated, based on which condition, how they operate, and whenever it is unnecessary or undesirable, we have to try to remove those. And if we need to produce those, we also have to have the capability so that we can introduce those, so that we can have our desired goal. So we have to know the way out of these limit cycles completely, how to remove or how to bring those based on the fact that whether they're desirable or undesirable. And next one is called the response of the van der Pol equation is also being shown in your figure 1.4. I'll advise you to go about that one. They have just shown the two scenario, that whatever your starting condition, eventually whatever the response, it will be following. So whatever you're starting, eventually it will going to merge with the oscillation. Okay, so eventually it will be following the same path. So just let it have a look at that one. So next nonlinearity that is available is called a bifurcation. Uh, Bifurcation. So what is bifurcation? Bifurcation is as the parameter of the nonlinear dynamic system are change, the stability of the equilibrium point can change as well. Also the number of the equilibrium point can also change. So the values of these parameters at which the quantitative nature of the system motion changes are known as critical or bifurcation value, and the phenomena is known as bifurcation. So this is the definition. What you can come up from this definition is, if the system parameter is changing, then system stability of this equilibrium point can also change. The number of the equilibrium point can also change. So if something like this is happening, then we call this phenomena as a bifurcation. And the value for which this is actually happening is called bifurcation value. So uh, they try to explain. So system parameter, the reason is system parameter changing, system parameter changing. And what is the cause? The cause is uh, change in equilibrium points, number of the equilibrium point, number of equilibrium point can change. This is one, and two is the stability condition of this equilibrium point. Condition of equilibrium points can also change. Okay, so one example is given using the one of the mechanical system is x double dot equal to alpha x plus x is x cube. equal to okay, so sorry, it's download pass. Okay, equal to 0. So this is called hardening spring problem. So if the spring is becoming hard, then this is what is happening. And in this case, as you can see, there is d by dx is not, dx by dt is not available in this equation. So what does it mean is that it doesn't have any damping available, so it will have a sustained oscillation. So now if you can try to find out the equilibrium point, as you can see, x double dot has to be equal to 0. So alpha x plus x cube equal to 0. So from this one, we can see that our value of x should be 0 root over alpha. Okay, so to minus root over alpha. Okay, so based on the value of alpha, we have these three scenarios. So, but one thing you have to be careful, if you take one of the x, what you have is x square minus alpha, x square plus alpha. Okay, so definitely x equal to 0 is one of the thing, x square equal to minus alpha is another thing. So it cannot have a negative value. So if you now take the range of alpha from sorry, it cannot have an imaginary value. So if you take the range of alpha from say positive to negative, so if it is positive to negative, what does it mean is alpha, this is alpha, and this is your XA equivalent, so equilibrium, so XC. So if you take from positive to negative, if the value of alpha is positive, then since it cannot take any imaginary value, there is only one equilibrium point at 0. And now once the value of alpha is negative, we are in this axis. So now if the because of the negative value, and this one is also negative, now we can have actually x equal to uh, minus root over alpha as well as plus root over alpha. Okay, so now what we have is we have a something like this. We have three different distinct lines, okay, based on the values of alpha. And now this line is previously this was stable. Now this is what is becoming stable. Okay, this is stable. So this line here actually becoming unstable. Now, this is a classical example. So the solution is not provided, but this you have pictorially given this curve. So this kind of curve, since it is similar to mm, pitchfork, so this kind of bifurcation is known as pitchfork bifurcation. What we can see here is basically there was only one stable point for negative values of alpha, which was 0. And now for highest, for positive values of alpha, there is basically three, sorry, for positive values of alpha, there was only three solution possible now. And also, as you can see, the equilibrium point is divided into three equilibrium. One equilibrium point is becoming three equilibrium points. So this point, alpha equal to 0, is actually your bifurcation point, bifurcation value. Okay, so this is one kind of it. There is another kind of one is possible bifurcation change of it, which also introduces limit circle. So it is not only becoming stable here in negative side of alpha, rather in the positive side, what is happening is you have a system like this, and then you have a limit cycle, a pure oscillation cycle, something like this. So if you have any oscillation in this stable zone, so if that oscillation is being generated, it will eventually will go into that stable point. But if anything is generating here, it will actually eventually will reach to the limit cycle. So this is your the circular thing is actually called the limit cycle. So this is the direction. So anything generated in between, it will be eventually going to the limit cycle. Pure oscillation. So this kind of bifurcation is known as half bifurcation. So we'll be discussing in detail with those limit cycle bifurcation thing in some advanced classes. So next thing is the chaos. Chaos. What is the definition of the chaos? Is small differences in initial conditions sometimes can cause in linear system causes a small change in the output. Okay, so but in case of this nonlinear system, a small change in the initial condition can give a large change in the output condition, and though that is what is known as chaos. And what does it actually means is the system output is extremely sensitive to the initial condition. So a small change, like say your initial condition was x equal to 2. So in linear system, if x equal to say 1.9 or 2.1 or say 0.1, 1.99. So for this small change, there will be very hardly any change in the output. So they'll be almost identical. But for a nonlinear system, this small change can introduce large changes in the output. So this is what is called chaos. And chaos, one of the critical essential feature of the chaos is unpredictability. So it's very difficult to predict what is happening there. But we should also distinguish the chaos from the random signal, random motion. Basically, random motion. The problem with the random motion is the time derivative of the random motion is cannot be predicted. But in case of the chaos, the time derivative of the chaos is also deterministic. So this is only the difference between them. So one of the example of the chaos is actually being given, a mathematical example in the book is having this equation x double dot plus 0.1 x dot plus uh, x to the power 5 equal to 6 sine t. So this is your input, a sinusoidal input. Now they have used two example, x equal to 2 and x dot. These are the two initial condition of the position as well as the velocity is 3. Now they have seen that if they just change slightly the initial condition from 2 to 2.01 and 3 to 3.01, so the system introduced some undesirable effect of your system. I will actually advise you to have a look at the figure sorry 1.1.6. So they actually figure in this figure two sinusoidal waves are given. The input wave is given, and based on that the output is given. So initially, even though the output seems same, but gradually in the later part after certain time, it seems that two different distinct output is coming, which is definitely unpredictable in nature. And this is the thing. So one of the physical example is the turbulence in the fluid mechanics is one of the thing, and also is the example of the chaos, and as well as the ambient atmospheric dynamics is also a chaotic behavior. That is why making a long-term weather prediction is impossible. Okay, so some electrical and the mechanical system also exhibit this chaotic nature, like as you said, the backlash, aeroelastic dynamic, wheel trail dynamics in the railway system. So all these are actually an example of your chaos. Chaos also occurs mostly in strong nonlinear systems, so highly nonlinear system. So for a given system, if the initial condition or the external input can cause the system to operate in a high nonlinear region, then it is probable that there is a high possibility as well that there will be chaos involved in this system. So if your nonlinear system somehow is very sensitive to the initial condition or external input changes in these parameters, in that case, the system can also have chaos. So chaos is also undesirable, and because of which we should be carefully analyze this characteristic, and based on that we actually have to try to eliminate those effects, those who are actually causing the system stability. Okay, so next is so there are some other behavior also sometimes available, like subharmonic generation or jump resonance, frequency, amplitude dependency of your field vibrations. So all this kind of thing is also there, but most commonly the points that we have discussed, the topics that we have discussed that commonly occur, and out of which the limit circle is one of the most important one we are actually supposed to discuss. And so we'll continue with the chapter 2 from here. And chapter 2 is basically the phase plane analysis, and we'll see the linear and the nonlinear version of that phase plane analysis as well. So it is almost, I think, elapsed 1 hour has elapsed already. So let us stop here. And this is, as I said, this chapter is a fundamental background knowledge that we need to go for the nonlinear analysis, what types of nonlinearities we have, why actually nonlinear analysis is a must-learn thing nowadays because of high computational power we have nowadays. So let's stop here today's class, and let's see you in the next class soon, inshallah.